welcome back to Honors Topics in Physics. And so today what we're going to be talking about is friction. What would life be like without friction? Is friction a good thing or a bad thing? You might be tempted to say that friction is a bad thing because it reduces the efficiency of a lot of different mechanical operations, such as engines and things like that. But it'd be awfully hard to walk without it. By awfully hard, I mean impossible. If you picture them oiling the floors and with the slickest, lubricatiest stuff that you think of, and you tried to walk, you wouldn't be able to go anywhere, just like on ice. Okay, so friction is both a good thing and a bad thing, like most things in life. It's got advantages and disadvantages, so it's not just one or the other. So do you guys remember from middle school that energy cannot be created or destroyed? And a moving car has kinetic energy, right? Remember from before. Where does that energy go when the car comes to a stop? What happens to that energy? Okay, it's not converted back to potential. Okay, well that is if it's just on a level street. If it just rolls down a level street and uses its brakes and comes to a stop. The energy isn't converted to potential, it's converted into heat. Okay, now that energy is not destroyed. Heat energy is not destroyed. It's just in a form that's harder to use for various other operations we would like. What causes friction? Well, if we were to zoom in on any surface, even surfaces that appear pretty smooth, such as well, I mean any surface, but such as a piece of paper, or like the surface of a credit card or something like that. Even surfaces that appear very, very smooth, they're very rough on the microscopic scale. They've got all kinds of hills and valleys and bumps and lumps and things like that. Okay, and when you try to slide, so this is to represent one surface and this is to represent another surface. If you were to try to slide one past one another, what you would see is a bunch of teeny weeny little normal forces. Points of contact that are that oppose the motion of the sliding of that object. So that's what causes a lot of friction. There's other things too. There's another component, and that is that some surfaces tend to be sticky towards one another through attractions that you'll learn more about in chemistry. So there's also that dipole and various other types of interactions. There's two main types of friction. One is called static friction, and the other one is called kinetic friction. And that's because friction does one or two things. It opposes a surface from sliding. It prevents sliding, such as this box, which is not sliding down the hill. And there's still friction with this box, which is sliding down the hill. And friction is opposing that motion. Okay, so friction opposes motion that is impending. Okay, and if there was no friction, this would slide down. So friction is preventing that motion, or the sliding of two surfaces. It's always opposite that. So, and these two types of friction that are involved here are static friction and kinetic friction, sometimes called sliding friction. Static friction is when the surfaces are not sliding past one another, and kinetic means motion, kinetic energy, think of, and that's when the surfaces are sliding past one another. They're slipping. Okay, so you need to be familiar with those terms. Static, I think everything is static means it's not moving. Kinetic means moving. So those are the main difference. So this is normally when we would do a lab, but we're just going to kind of recap what we should have found with the lab, and I'm just going to kind of give you the answers. So the force of friction, and you should be familiar with these 5 things, depends on the materials in contact. Okay, the rougher the material, more friction. Okay, the rougher the materials, the greater the friction. That makes enough sense. The greater the normal force between the surfaces, the greater the friction. Static friction tends to be greater than kinetic friction. Or static friction maxes out more than kinetic friction. Okay, so static versus kinetic. And it does not depend on these. It's just important to know what it does not depend on. It does not depend on the area of contact. So if you have a small block in contact with the desk, it does not have more friction compared to a large area of contact, all other things being kept the same. And it does not depend on the speed of movement. Once an object is moving, it's kinetic friction, and it doesn't really depend on how fast it's moving once it is moving. So this is the equation. Go ahead and jot this down. We're not going to do much with this equation, but jot it down so you've got it. So the force of friction, and this will be an equation that'll be much more important in later physics classes that you take, AP notwithstanding. So the force of friction is equal to mu. This is called the coefficient of friction. It's a Greek letter, lowercase m, and there's just tables of numbers of these, and it's based on the materials in contact. So there's a coefficient of friction between wood and steel, and rubber and polyethylene, and et cetera, et cetera. There's just tons of these different coefficients of friction, and they're just determined experimentally. They just get the materials together and they see how much friction occurs, and then they calculate what the mu is. And then this is the normal force. This is the normal force between them, which is pretty much how hard the surfaces are being pressed together. So the harder the surfaces are being pressed together, the greater the normal force and the greater the force of friction. Okay. So why is it the normal force and not just the weight of the object? In some cases they're the same. For example, we've got a crate that's sitting on a table or whatever. Everything's static, it's stationary, so there's a force of gravity down and the normal force, they're equal. The table's pushing up equally as hard as gravity's pulling down on the crate. So in some cases they're the same, but in some cases they're not. Let's say I put a rocket, and now my rocket is pushing down on the thing. Which, and this is, other than the fact that it's a rocket, is a reasonable scenario. So if you press two surfaces together, friction is going to increase between them. Okay, so that rocket is going to increase the normal force. If you were to press down with your hand, you would increase the normal force and increase friction. If you were to lift up on the object, you would decrease the normal force instead of pushing down. And if you were to set the surface at an incline, okay, the normal force is not the same as the weight of the object. It's going to be less because it's only that component of gravity, that partial component of gravity. Okay, so these are some examples of coefficients of friction. Here's the coefficient of static friction. These are the coefficients of static friction for two materials, and then this is the coefficient of kinetic friction for the same materials. So you notice that if we look at rubber and dry concrete as greater friction than rubber and wet concrete. So these are chosen specifically to deal with cars. So basically this is why, since you've got less coefficient, a smaller coefficient of friction, this is why your tires are more likely to peel out during when the roads are wet. The roads are wet. And you notice that the coefficient of static friction is greater than the coefficient of kinetic friction. Remember, we said static friction is greater than kinetic friction. So we see that this is supposedly the engine. So the coefficient of friction was steel versus steel on a dry in the engine is 0.78, which is pretty high. When you introduce oil, it's down to 0.15, and then once it's already sliding, once it's already moving, it's down to 0.06. So it's really, really small amount of friction. And those engine oils have been engineered to provide the best lubricity as they can. This is kinetic friction on your auto brakes. And what you see is while your brakes are wet, you're less able to brake the car. This is not even anything to do with the fact that the rubber in the road, this is in the actual brakes themselves. So while that's wet, you've got less friction available to slow your wheels down. So okay, so we covered a couple things. Why it's the normal force. We've covered static is greater than kinetic. Coefficient of friction, it depends on the materials. Why are rougher materials, why is friction greater for rougher materials than smoother materials? Well, if you were to zoom in on rough materials versus smooth materials, you could see that it would be much harder to slide this surface over, this top surface over this bottom surface, much harder if these surfaces are jagged and deeper and all that. So that, I'm sure, makes enough sense anyway. Okay. So one thing to note is what you would have noticed is that when you pulled on, what you would have had is a wooden block and a spring scale, and you would measure the force of friction required to get that wooden block to slide by pulling on a spring scale. Is that when you pull on the block would have pulled back a little bit. If you pulled on the block harder, it would have pulled back harder, and the spring scale would read more. And you would pull harder and harder and harder, and then eventually you would reach a point where it slipped. Okay, and then once it slipped, then you were sliding along in kinetic friction. So this would be static friction when you're pulling and the block isn't moving. Okay, and then once it slips, okay, this is when we drop down to kinetic friction. What about this question? Some people have been known to let some air out of their tires. Let's say this is a properly inflated tire, okay, and this is a tire where we've let some air out of the tires, and it's kind of flatter, okay. And the thinking that you're going to drag race faster if you let some air out of your tires is that you get this flat spot that forms on the tire with less air. And that this flat spot is going to give you more area of contact between the road and the tire, which is going to give you more friction, which is going to cause you to accelerate more quickly. What does theoretical physics say about that? Is that going to make a difference? Okay, having more area, does that increase friction? It's not in my friction equation. Okay, so no, it really shouldn't. Although there's probably some other factors. This may actually speed your tire up due to the fact that this tire is deformed and it's having to work against the deformation of the tire. But it just due to the area, it really shouldn't make a difference. Okay, and that is that for the day. Thank you for following along, and see what else is attached to the lesson today.